Thanks. Hey, good afternoon, everyone, and welcome to the BALPA Met Office Space Weather webinar. I'm Graham Smith. I'm part of the BALPA's ATMA group. That stands for Air Traffic Management and Airfields. And on behalf of that group, I take an interest in space weather and volcanic ash. As far as aviation goes, until quite recently, space weather was only really a factor for HF communication and cosmic ray exposure. With the proliferation of GNSS approaches and GPS in general, it's become a much more critical topic, as solar activity can also affect the satellites that provide the GPS service. The UK Met Office have become world leaders in the field and produce some very detailed forecasts on the level of solar activity and the possible effects on ground, air and space-based equipment. Today we're very pleased to have not just one, but two experts in space weather, Mark Gibbs, the head of space weather at the UK Met Office, and Krista Hammond, senior account manager, space weather. Mark has been with the Met Office for over 30 years and has had many roles, including flying on the Met Office's atmospheric research aircraft. From 2010, he led the development of the Space Weather Programme, including setting up the Met Office Space Weather Operations Centre. It's only the third centre globally to be staffed 24/7 and provides advice to government, industry, defence, international partners and the public. In 2021, Mark became the head of transport within the Met Office, covering aviation, maritime and land services. Krista initially joined the Met Office as a meteorologist, then trained as a space weather advisor shortly after the Met Office Space Weather Operations Centre became operational. In 2019, she became the senior account manager for space weather. One of her particular interests is end user engagement, working with various sectors to help them understand the risks of space weather. She leads on the Met Office's outreach and exercises within the aviation industry, and as an advisor to Mark, who is the ICAO Met Office panel member. This presentation should run to about 45 minutes or so, and there should be time for a question and answer session at the end. I'll be joined by Stuart Clark of the ATMA group, so if you do have questions, could you direct them to Stu and he will collate them and send them on to me. As usual, this webinar is being recorded and should be available via the BALPA website for offline viewing. That's more than enough for me just now, so I'll pass you over to Mark and Krista. Mark.
Okay, thank you, Graham. So I will just start showing my screen. So I will be sort of presenting the first half of this, and then I'll pass over to Krista, who will finish off the presentation. And are you seeing my?
Yep.
You're seeing my slides? Yes. Okay. Should be full screen now. Apologies, we don't use Zoom in the Met Office. We're teams and organisations, so we're not particularly familiar with it. Are you seeing it full screen?
It's not full screen for me.
Oh, okay. How about that?
No, it is, yeah.
Right, okay. Well, thank you for this opportunity to speak to you and all the various people online. So, as Graham said, we'll take you through space weather, some particular aviation-related applications, and then happy to take any questions at the end. So, what is space weather? Space weather is pretty much invisible. The physical manifestation of space weather, though, is the aurora. You know, perhaps one thing which is on everybody's bucket list, and I suspect probably many BALPA members, certainly those flying perhaps high latitude, yeah, across the Atlantic, may well have seen it from time. In reality, what we're concerned about, so space weather is basically, the dynamic environment that we get from the sun. So a mixture of electromagnetic radiation, charged particles and charged plasma. And we're really interested in those effects on the Earth and near Earth environment. So we're thinking about solar flares, which produce radio blackouts, HF communications, radio blackouts in particular. They travel at the speed of light, so they are here within 8.5 minutes. But generally, the effects of those last minutes to a few hours. We also have solar radiation storms, which are produced by energetic particles being accelerated near the sun. Those can arrive within a matter of a few tens of minutes, but often can take a few hours to arrive at Earth. And again, the effects tend to last hours, possibly to a day or two. And last but not least, we've got geomagnetic storms, which are driven by produced by coronal mass ejections. They typically take the order of 2 to 4 days to travel the Sun to Earth distance, the 93 million miles. But the fastest on record has done it in about 15 hours. And again, yeah, as they take 2 or 3 days to arrive here, the effects can typically last 2 or 3 days. So as a general rule of thumb, their sort of time of arrival from the onset of the Sun to arrival at Earth is broadly consistent with the amount of time the effects last at Earth or persist at Earth. So in terms of the solar flares, you see bottom right there, solar imagery we look at, you see that bright flash on the left-hand side of the solar disk there. So that's a solar flare occurring, so that's a burst of electromagnetic energy. We detect it in the X-ray wavelength. You see that the top plot there. And the most notable impact is causing increased absorption in the D region of the ionosphere. And that middle plot showing sort of the bull's eye over sort of the equatorial area and over the Greenwich meridian is showing the effect on HF radio communications of a solar flare. So this was an actual event back in September 2017, and you see it is by far the lower frequencies which are impacting more than the higher frequencies. Alongside the HF communications impacts, you can also get a degree of satellite communication interference, radar interference, particularly over the horizon radar. You can also get some satellite orbit decay, and you can get some GNSS errors, particularly in single channel GNSS systems. Solar radiation storms. So these are, as I said earlier, particles being accelerated close to the sun to near relativistic, can't get my words out, to near relativistic speeds. Depending on how well the source region on the sun is connected to the Earth will depend on how quickly they arrive. So a well-connected area, we will see those particles arriving in probably the order of about 10 minutes or so. Less well-connected areas can take sort of several hours, potentially up to a day. As I said earlier, typically the effects of these last a few days. So particularly in the polar regions, they can cause high latitude radio degradation, can cause satellite disorientation. So two images on the right, the top blue one is an image we use in space weather forecasting, and all those blue speckles, like the old analog TV signals that I remember from my childhood, each one of those is an energetic particle hitting the CCD array, which forms the camera. Bottom right is actually a space weather satellite operated by NASA, which you can see the bombardment of energetic particles hitting the satellite. And a lot of satellites basically carry star maps and have star trackers and orientate themselves by comparing the stars they can see with a map they have. But obviously each one of those specks looks like a star, and in this case the satellite didn't know which way up it should be, and it sort of went into a gradual roll, as you can see. It can also cause spacecraft damage, particularly to satellites in Earth orbit. But of particular interest to this group, it can produce high altitude radiation exposure. So that's in addition to the galactic cosmic radiation background we're getting all the time. And can also cause upsets to electronics. So that's both avionics, potentially on board aircraft, but also we do see these effects come all the way down to the ground. So we can get some impacts on ground-based electronics as well. When they come down to the ground, we call them GLE, ground level events or ground level enhancements. So essentially the particles come into the top of the atmosphere, and then essentially there are nuclear collisions high up in the atmosphere, and that produces a whole range of daughter particles which come further down. Many of you probably know that the radiation we dose we get from galactic cosmic radiation is actually anti-correlated with space weather. So when we're in periods of active space weather, the galactic cosmic radiation goes down, and when we're in periods of low space weather, you get higher levels of galactic cosmic radiation. So as you will see in a few slides' time, we are approaching solar maxima. So actually galactic cosmic radiation is lower than it typically is. However, during this period of active space weather, we have the risk of getting these solar energetic particle events coming in. So they can produce human radiation dose for anybody who is flying at high latitude and high altitude. There's potential to disrupt aircraft avionics, and that's an area which is actively being investigated at the moment, but also said potential to disrupt electronic ground-based systems as well. In terms of space weather, probably the thing we worry about the most is these coronal mass ejections, which are exactly what it says on the tin. They're ejections of mass from the sun's corona. So these two images you see videos running on the screen are what we use operationally. So we occult the sun, so we block out the very bright light of the sun so we can see the very much fainter light. And you can see these sort of bubbles of magnetized plasma coming off the sun. Each one of those is probably the order of about 1 billion tons of material, and it can be fired out in any direction from the sun, and it comes out effectively. You want to think of it like a cone, a bit like an ice cream cone coming out from the sun, and they typically have a width of about 40 or 50 degrees. So we can get events like this which erupt from the sun and don't impact the Earth, and obviously other events which do impact the Earth. And that's one of the key things that space weather forecasters are trying to do, is look at the direction they're going in and also try to predict their arrival time. Because I said earlier, the arrival time can be anything from about 4 or 5 days to 15 hours. And obviously, that difference is quite critical. So it's these CMEs which produce geomagnetic storms. So as I said, it's magnetized plasma. So there is the local sun's magnetic field actually captured within this plasma, and we don't know the orientation of that magnetic field. If that magnetic field is headed towards the Earth and is effectively the same polarity as Earth's magnetic field, i.e. north at the top and south at the bottom, then like with bar magnets, if you bring two like poles together, the magnetic energy would largely pass around the Earth and we won't see significant impacts. However, the polarity comes in the opposite way around, like south at the top and north at the bottom, then again, like two bar magnets, the magnetic fields combine and we get magnetic energy entering the Earth's magnetosphere. So that produces the aurora, which is the pretty side of space weather, but it can cause a whole range of problems. So an incoming CME will disrupt the ionosphere. So that will cause problems with VLF to HF radio communications and satellite communications. Can produce spacecraft charging, so produces problems in terms of the spacecraft operation. Can cause radar interference. Due to the disturbance of the ionosphere, it may be difficult to pass GNSS signals through the ionosphere. Either completely, we get complete loss, or alternatively, it can be the signals can be deflected, and effectively we get errors in location and timing. We get spacecraft orbit decay due to expansion of the neutral atmosphere. And the thing which really brought space weather to the attention of the UK government is it can produce currents in long conductors. So things like power grids and railway lines are very efficient long conductors which get induced currents in them. As I said earlier, the effects of these of a CME arrival will generally last for a few days, that sort of order. I mentioned the solar cycle in connection to galactic cosmic radiations. So we effectively have an 11-year solar cycle on average. You see there on the left, sort of the the solar cycle, which is actually the count of number of sunspots actually on the sun, just going up and down on a regular basis. We are approaching the maximum solar cycle 25, so we expect the maximum to be at some point this year in 2024. Can only tell you when we've reached the maximum after we've gone past it, and we see we're very much on the declining phase. What's important to note though, and the graph on the side tries to show, is each one of those strips is a solar cycle going all the way back to the 1930s. The sort of red shaded areas is where the solar maxima occurred, and the blue shaded areas where the solar minimum occurred. We've got the minimum in space weather activity. And those blue bars show where we have significant events, in this case, significant geomagnetic storm events. And I think you can see, it's fair to say they don't just cluster around the maximum. You can get storms at any point in the solar cycle, but they do tend to occur more likely close to the maxima and then in the declining phase, and that period between the maxima and the minima. So looking a bit more detail at the projections for the current solar cycle. So the red shaded area there shows what the original forecast was, and we're currently running well ahead of that original forecast. So you see that black line shows the actual sunspot numbers, and the purple line is a smoothed average of that. So you can see we're running quite a bit ahead, both in times and also in terms of magnitude. So we are expecting this to be a bigger than anticipated solar cycle with more activity. But as I was saying, when we think about impacts and impacts at Earth, we're really just now entering the period of most concern. So really from now for the next 4, possibly 5 years is when we're at the most impactful period of the solar cycle. So space weather sits on the UK's National Risk Register. It's been on there since 2011. The latest edition was published in 2023, just under 12 months ago. And you see circled there is risk number 47, which is severe space weather. Essentially on that graphic, the vertical axis is impact and the horizontal axis is likelihood. So the really bad stuff which occurs more frequently is top right. The less bad stuff which occurs infrequently is bottom left. So as you see, space weather is quite close to the top right. So it is a significant risk. You can see some of the other risks which occupies the same sort of box as space weather. And the question everybody asks is what's 54, the one above it? And that's, no surprise, pandemic. So it just goes to show where it sits. Obviously, we all know the impacts of pandemic. Many of us, particularly in this industry, will remember the impacts of the volcanic ash events of 2010. And volcanic ash is a box below space weather. So we anticipate a major space weather event having a bigger impact on UK PLC than that volcanic ash event of 2010. Perhaps what I should just say when talking about a major event, we're talking of a 1 in 100 year event. We base our reasonable worst case scenario, which you use for doing these national risk assessments, based on the 1859 Carrington event, which is the largest recorded event we have in history, which is of the order of about 1 in 100 years. Just looking back at historical impacts, I've already mentioned the Carrington event of 1859. Back then we didn't have the technology we have nowadays. The technology of the day really was the telegraphic system, and we saw some fairly significant impacts on the telegraphic system, including the fact that they can actually operate it without the batteries connected to the system, such was the induced currents being produced in those long conductors. Just thinking about more contemporary events, back in 1989 in Quebec in Canada, we had a total power collapse across that province, where a large CME caused basically automatic systems to trip on the power grid, which prevented the grid being damaged. But in 94 seconds, it means the whole of the grid across the whole of the Quebec province shut itself down. Good thing was that shutting itself down to protect itself meant that it could be recovered in a matter of hours. If it had been damaged, it would have taken days to weeks to recover that. So yes, there's a good example. And then again in Malmö in Sweden in 2003, they had a complete power blackout across the city of Malmö. There weren't really any much in the way of space weather services then, but the electricity operator in Sweden said if they had had a forecast of it, they could have prevented that power blackout. So obviously music to the ears of an organisation like the Met Office. And during that event, there was 47 satellites having temporary outages. So obviously, as time goes on, we're getting more and more satellites, and we're becoming more and more reliant on the services they provide. So that is, really a key turning point, seeing those satellite impacts. In recent times, certainly the time since we've been doing space weather in the Met Office, which goes back to sort of 2012, the largest event we've had so far occurred in September 2017, which was quite a minor event, to be perfectly honest. And there we saw 3 electricity transformers tripped out in Scandinavia. There's no customer impacts, but it just goes to show that even quite small events can produce effects. And there was an Air France flight flying across the Atlantic from Brazil, I think it was from memory. And because of the degraded HF radio communications, there was no contact with that aircraft for over an hour and a half whilst it was mid-Atlantic. So obviously that caused some concerns. Right, so I'm going to hand over to Krista now. So I will stop sharing and then Krista will pick up from here.
Excellent, thank you. Let me share my screen. And just to check that you're seeing that in full screen mode.
Yes, we are.
Fabulous, right. Okay, so I'm going to now move on from where we've seen those historical impacts, some impacts that we've seen recently, and also what we could expect to see if we had a severe space weather event in the UK, and then cover the forecasting that we do in the Met Office, both the sort of day-to-day MOSWOC forecasting and that which we do specifically for aviation as well. So to begin, as you probably saw from one of Mark's slides, which showed the last solar cycles, we haven't had any of the most severe space weather that we can get. So with geomagnetic storms, the storms go on a scale of 1 to 5, with 5 being the strongest, 1 being, sort of the lower end of that scale. We haven't had any of those upper end, those G5 storms, for about 20 years. But what we're seeing is the more that we're relying on technology and systems which are impacted by space weather, we're seeing impacts even if we aren't getting those most severe space weather storms. So there have been some recent space weather impacts even within the solar cycle. So these impacts are all from last year, from 2023. In February, we had a period of G3 geomagnetic storming. So that's considered strong, but on a scale of 1 to 5, that's sort of middle range geomagnetic storm there. Some impacts that were reported from that, though. In Canada, drilling ops were disrupted across several fields. So the operations were paused during the geomagnetic activity. Now, there's reasons why drilling can be disrupted. One of them is the geomagnetically induced currents, this current which can form along the Earth's surface during a strong geomagnetic storm. But in this case, it was most likely that the GNSS, which was being used for precision drilling, became not reliable enough to continue drilling. So drilling was suspended for a period of hours. During the same storm, SpaceX's Starlink delayed launch. This was to avoid possible atmospheric drag. SpaceX launched into very low Earth orbit, which is impacted by atmospheric drag during geomagnetic storms. In 2022, SpaceX launched into a moderate geomagnetic storm. They launched 49 satellites and put them into safe mode when they experienced increased drag. And because of that, they were unable to, because of the space weather conditions at the time, they were unable to take 39 of those satellites out of safe mode, which then re-entered the Earth's atmosphere and burnt up. So Starlink lost 39 out of 49 satellites in 2022. In 2023, they delayed a launch because of geomagnetic storming for this reason. Another impact was the International Laser Ranging Service, which is a global satellite which provides global satellite laser ranging data. We're reporting ranging errors by around about 100 meters. Then in March, we had a spell of G3, G4 storming, and more relevance to aviation here. We had reports of disruptions to EGNOS, the GNSS augmentation system in Europe, caused by severe space weather on the 23rd and the 24th of March. This was reported across Iceland, Portugal, and Spain, and it appeared that the NOTAMs weren't being displayed correctly as well. Later on in the year, we actually experienced further instances of G3, G4 storming, where we again got reports that EGNOS was being degraded, as well as the US equivalent during that time. And then in April, the 23rd and the 24th of April, again, G3, G4 storming. So, G3, 4 out of 5. Prestwick, NATS at Prestwick reported they were unable to contact aircraft north of 57 North overnight on the 23rd. And on the 24th, we're having to use higher frequency than normal to contact aircraft. So these are some recent space weather impacts that we've seen. To get an idea then of what we could expect if we had a more severe space weather event, that 1 in 100 year event, which Mark was mentioning in his part of the presentation there. So using the Carrington event as a benchmark, the Royal Academy of Engineering produced a report back in 2013 to assess the risk of what a severe space weather event would be to the UK. And these are what the findings were then. So in regards to the impact on the electricity grid, it's expected that around about 13 transformers would be damaged across the UK. A space weather typically impacts areas further north most. It's estimated that 7 of these would be in Scotland and 6 across the rest of the UK. As well as this, there's the risk of coastal nodes experiencing disconnection and voltage instability, so rolling outages of hours in urban areas as well. So that's the impacts that we would expect to the electricity system. In terms of satellites, it's estimated that around about 10% could experience temporary outages for hours to days, and those satellites in orbit also experiencing rapid aging. As Mark mentioned in Malmo, in the event in 2003, where we had the Malmo outages, 47 satellites were damaged during that. I had a look, and at the time there were around about 800 satellites in orbit at the time. Now there are around 9,000 satellites. So 10% of satellites is a really quite substantial number these days. The loss to GNSS is something which is increasingly problematic as we become more reliant on it for position, navigation, and timing. And it's estimated that we could lose GNSS, either complete or partial loss, for up to 3 days. And then in terms of communications as well, there's the loss of SATCOM and HF communications during a severe space weather event. This diagram here shows you impacts which were reported during a space weather event back in 2003. I'm not going to go through all of these impacts because there's clearly quite a lot, but what this shows is that when we get a severe space weather event, the impacts are not just confined to one area geographically. Space weather is a global threat, it has global impacts, and we work together globally with partners to try and understand this threat. So just to pick out a few of the impacts which were reported during this storm, known as the Halloween storm back in October 2003, they were polar flights which were rerouted. HF comms outages were reported across the African continent. It's covering the entire globe. The impacts felt here, so down over Australia, there was SATCOM and HF outages reported as well. So the impacts that we can see from space weather are broad-ranging, both in terms of the systems that they affect and also in the geographical locations which this covers. This is an excerpt from a report from the Space Environment Impact Expert Group, which is a UK group who advise government on the risks of space weather to the UK. And this gives an idea of what we could expect to see during a period of intense space weather. So it's estimated the longest interval of severe space weather is likely to be in the order of 2 weeks. And this is kind of the critical bit. I'm coming from a forecasting background, this was an important bit for us. It is very difficult to predict the exact order, size, and duration of space weather phenomena. So we have solar flares, we have radiation storms, and we have geomagnetic storms. It isn't just a case that in a severe space weather event, we would see one large solar flare, one solar radiation storm, and one severe geomagnetic storm. We could be getting these sort of a mix of phenomena and a mix of impacts over a course of a 2-week period. This means that different systems could be experiencing impacts simultaneously, sequentially, or unpredictably, so effectively randomly. Furthermore, it's highly likely that these failures will interact with each other, which cause cascading failure modes, which are fundamentally difficult to predict. So space weather impacts many systems, and the exact impacts on those systems are often very difficult to predict in advance. It's because of these risks that the Met Office Space Weather Operations Centre is in operation. It was set up in 2014, so this is our 10th anniversary this year, and it is a forecasting position within the Met Office Operations Centre. We have 24/7 staffed operations, so there's a space weather forecaster on duty day and night monitoring the sun for signs of activity, which could lead to severe space weather. We are one of the 3 key global centres. So when we first were set up, there was 2 centres in the US. There's the Space Weather Prediction Centre, who are responsible for civil predictions in the US, and the US Air Force 557th Wing, who do forecasting for the defence side of things. There are more centres across the world being set up 24/7 as other countries are also realising the risks of space weather to technology and infrastructure. We have operational coordination between the 2 US centres and also other key global partners as well. Within the Met Office, we support a range of sectors. So we support government, military, we do public forecasts, critical sectors, and we also are one of the centres within the ICAO service for space weather. As well as our operational meteorologists, of which we have around about 14 to cover the roster, we've also got a team of scientists who specialise in research to operations. We've got user engagement and programme management, which is where I sit, and IT developers to make sure that our forecasters have everything needed to maintain these 24/7 staffed operations. As well as observing the sun, we have a range of forecasting models. One of them is shown there on the top right-hand side. It's known as ENLIL, and it's a model showing the solar wind. And we can see the solar wind getting pushed out from the center of that circle. The sun's in the center, and the spirals is the solar wind coming out from the sun. If we see a coronal mass ejection, we can make measurements of how fast that coronal mass ejection is traveling and the direction. And by plugging that into this model, we can then get an idea if that's coming towards the Earth, and if so, given an estimated arrival time as well. By monitoring the sun, by using a range of models, we're then able to provide some forecast information, which should help critical sectors to make decisions and mitigate against the worst of space weather events that we could see. I've got some examples of some forecasts that we produce here on a daily basis. The first being our forecast bulletin. This is known as a plain language bulletin. It's available on our public webpage as well. What this does is it gives an overview of the space weather we've seen over the last 24 hours and a forecast out to 4 days. And that's for the risk of geomagnetic storms, solar radiation storms, and seeing solar flares. This is designed for sectors and users who are impacted by space weather, but don't necessarily have sort of a deep space weather understanding of the scientific background. On top of that, we then have a technical forecast, which covers the same things. It's still got the summary, it's got the 4-day forecast, but it's in a more technical language and is more designed for those users who have got that sort of the background science into the space weather as well. We will give a risk of seeing geomagnetic activity for 24 hours as well as the next 3 days based on whether we're expecting any geomagnetic storms off the back of coronal mass ejections. And then when we're experiencing space weather, we will send out a range of warnings, watches, and alerts. This one here is one which we send out when we start to get geomagnetic storming. The example here is a G4, so a KP8, and those are issued when those impacts are being felt here on Earth. Anyone can sign up to receive our space weather alerts and warnings. There's a link through just our public webpage. So you can find that either by going to the Met Office website, going under specialist forecasts, or just Google Met Office space weather and it'll come up there. And as you can see, just under the header, there's a request a specialist space weather account. And by signing up there, it's free. You just need to register for it. You can access pages where you can sign up to receive alerts and warnings. And we'll send out alerts and warnings for a range of space weather phenomena. And from there, you can sort of choose those alerts and warnings that you wish to receive, probably just focusing on the more impactful ones. We do have plans as well to start including an alert for when we experience ground level events, ground level enhancements as well due to radiation. Okay, and in terms of information which is available to the aviation community related to space weather, firstly to flag up a publication from the CAA, CAP 1428. This was updated a couple of years back to include information about the ICAO space weather advisories, which went live in 2019. And it's a publication which will provide with further information. It's a whole range of information there from what we've covered with what we mean by space weather, what the different phenomena can be, where the impacts can be felt, probabilities of occurrence, and also information similar to what I've just given about forecasting and observing space weather, both from the likes of MOSWOC as well as the ICAO advisories as well. It also gives information on how to produce safety risk assessments and a range of recommendations as well. I'll now cover the ICAO space weather advisories. So the ICAO service for space weather went live in 2019 with the intention to protect flight safety and also to minimize disruption. So it targets three key areas for aviation, those being disruption to HF communications, so the HF comms advisories, disruptions to GNSS navigation and surveillance, GNSS, and also to target radiation impacts on human health. So these are issued at two intensity thresholds, moderate and severe, as have been defined. And on the right-hand side there, I have a table which sort of breaks down the different physical effects that us as forecasters are looking for to issue an ICAO advisory. These advisories are issued when these thresholds are breached. So the format of the advisory is very similar to what we'd expect from volcanic ash as well. So just to quickly go through it, what it shows is the issue time and date, the Space Weather Centre who has issued the advisory. I'll explain the process just in the next slide here. The advisory effect, whether that's HF comms, radiation, or GNSS, where the space weather has been observed, and then a forecast at 6, 12, 18, and 24 hours. The remark should give a little bit more information. It tells us, it will say the type of space weather which is being experienced, as well as where the impacts can be felt. The way that the space weather global service works is that there are 4 global centres who are responsible for issuing the advisories for aviation. There's only one of them who is on duty at any one time. So there's 4 global centres. There is ACFJ, Australia, Canada, France, and Japan. That's a consortium. There's Pegasus, which is where the UK sits. That's led by the Finnish Met Institute. And there's around about 7 or 8 countries which are involved in that. The US Space Weather Prediction Center, a global center in themselves, and there's CRC, which is China and Russian Federation. At any one time, there's one center on duty. One center is on duty for 2 weeks, and they're responsible for issuing advisories for the whole globe. When the 2-week period is finished, they hand over to the next center. This means there's some redundancy. So if one center is experiencing issues, they will hand over to the following center, and the service should remain seamless to users. The advisors are issued through the standard distribution channels, so through AFTN. So the same way that you would pick up any of your standard Met products, you'd be able to pick up the ICAO Space Weather advisories as well. Okay, that's where we are, but quite a lot has changed in the last 10 years that the Met Office has had space weather forecasting capabilities, and we're always looking to improve, and there are some really interesting improvements coming through within the next couple of years. So I'm going to briefly touch on some recent work which has been done to fill in some capability gaps which we've had in the MOSWOC. So there's the SWIMMER program, the Space Weather Innovation, Measurement, modelling and risk, easy for me to say, programme known as Swimmer. This was a £20 million funded body of work split over 11 projects to address capability gaps within the MOSWOC. And this is producing new models, new measurements, and a new impact assessment. So starting with the modelling gaps that are being filled here, because there's a few which are relevant to aviation, and we've got some interesting models coming through which will help with our forecasting capabilities. So there's modelling of the radiation environment. That's not just for spacecraft, but also at aviation altitudes, and also giving an idea of where we can see impacts to electronic technologies as well. There's a new ionospheric model coming through, which will have a focus on GNSS and comms. So that will improve our modelling for PNT, position, navigation, timing, and communications. Linked to that, there's thermospheric modelling, predominantly for satellite industry for modelling re-entry, orbit determination, and collision risk. And more of relevance to the energy and rail industries, electric field modelling for power grid, gas pipelines, and rail networks to model that charge that we can get across the Earth's surface. But for radiation, for aviation, the radiation modelling and the ionospheric modelling will help with our modelling of the radiation risk and GNSS and comms disruptions due to space weather. There's also going to be observations which will support these monitoring and modelling. So we only really know if our models are doing well if we can use observations to verify those models. So for radiation, there's going to be sensor on spacecraft, which helps with that side of the modelling. But we're also going to be getting monitors, which will be at aviation altitudes, so that we can verify the new radiation environment models, which we'll be pulling through within the next couple of months. There's going to be a radiation testing facility to help manufacturers understand the vulnerabilities from space weather. And there's going to be also an update to the space weather impact study. The Royal Academy of Engineering report is very comprehensive, but that was back in 2013, and a lot has changed when it comes to our technologies and reliance on those technologies. So there's going to be an updated space weather impact study due out very soon. Just to focus on a few of the swimmer outcomes which are of most relevance to aviation. Firstly, we do have a radiation model for aviation altitudes, which was developed by the University of Surrey, which is in the final stages of verification and visualization. So our forecasters have access to it, and it's ready to become operational almost imminently. It'll help to support our commitments to the ICAO service, but we can just be using that to model the environment generally. In terms of new monitoring capabilities, we're going to be having new ground-based neutron monitors in the UK, one up in Shetland, one down in Cornwall. And this will help us to establish when we have these ground level enhancements, when we have a radiation risk which is affecting aviation altitudes. And we'll also have sensors which can be used on aircraft as well. Okay, I think that's all from me. So with that, I will stop sharing, and Mark and I will take your questions and answers. Well, we'll take your questions and we'll answer them.
I'll give my bit off. Well, fantastic. Mark, Krista, thanks very much for that. Absolutely fascinating. Huge, complex subject, and it's becoming much more relevant, obviously, in the current aviation industry situation. I've only ever experienced space weather myself via HF outages. And one time, I think it was probably around about 2003, I was in Denver and most of the computer systems went down, and that affected our dispatch. But just start the ball rolling. Presentation to pilots. We talked about the ICAO space weather advisories. How do we actually go about getting hold of those? EASA say that should be provided in our briefing materials, but anecdotal evidence is that the companies aren't doing that, and pilots have to go and find it themselves. And the only place I've been able to find it is on the Finnish Met site. Do the Met Office have any plans to make this information more accessible, i.e. through the General Aviation Briefing Service, etc.?
So I'll take that one, shall I? Yes, you're right. I would encourage any airlines to be getting their management to twist the arms of the flight briefing providers they use, because it is an Annex 3 service, and certainly the ICAO view is that providers shouldn't be picking and choosing which Annex 3 services they actually deliver to their customers. So I would certainly encourage anybody who's a pilot to be making noises within their own organisation. As you rightly said, information is available via the Finnish Met Institute site. I think NOAA SWIPSI also have a test site as well. We will be introducing it into our briefing services. So we are going through a process of rebuilding on our briefing services. So at the moment, nothing new has been going on there, but I'd anticipate space weather will be on there in probably the next 18 months. There's no excuse for any sort of flight briefing providers to not be providing it. It is available via SADIS, available via WIFs, so it is, the information is there, just down to them to present it to their customers.
Fantastic, good news. Oh, here's one. Do you know if the Royal Aeronautical, the RAE, whatever they stand for, do you know if the RAE is planning to publish an update to the 2013 assessment of the impact of a future Carrington event?
So there will be an update, but it won't be published by the Royal Academy of Engineering. So I think it was on the last but one slide, Krista mentioned as part of the swimmer project about there being an update. So we're expecting that to be available around about May or June time this year. It will be put out in the public domain, but it won't be published by the Royal Academy of Engineering. Having said that, I think virtually all the information in the Royal Academy of Engineering report is still correct. But obviously technology has moved on, so there's a few more things we've learned along the way. So I would still use the RAE report as useful tome. It is the global gold standard. Nobody else has done a similar study, but we should be seeing an update probably in 2 or 3 months' time, which we will make sure is publicised.
Grand, thank you. Where we go? Oh, cosmic radiation. That's another big one. It gets forecasted. Aircrew basically have laid down limits because they're part of radiation workers. However, passengers don't. Do you think passengers should be given a bit more information about the risks to flying polar routes than they are at the moment?
Oh, that's a good question. And probably one I'm going to duck, saying we're not the competent authority for that. So, we're certainly in discussions with the UK Health Security Agency, who are responsible for radiological protection. They do actually have information on their website for related to both galactic cosmic radiation, but also these space weather radiation events as well. And we don't predict GCR. It is quite predictable, except for when you get something like a supernova exploding. But we can't predict those. They've happened a long time before the energy actually arrives. But if there's a big space weather radiation storm, then I would anticipate that there will be readily available information from the UK Health Security Agency. But I certainly recognise that as an issue.
Okay, thank you.
Let's leave it there, shall we?
Yeah, very wise. Another one comes in is charging models. How's space weather research funded in the UK? There's quite a concern in Europe, especially among the ECA members, that there's no funding in Europe, there's no charging model for it, so the research will suffer quite badly. How does the UK get around this?
So in the UK, we're funded as a national capability by government. So currently by the Met Office owning department, which is the Department for Science, Innovation and Technology. What we haven't had though, up until now, is a research program. So Swimmer was the first project. As Krista said, we were originally produced forecasts in 2012 and went operational in 2014. I say it's like being marooned on a desert island. We had the capability, but we didn't have anything new coming through. We had no new supplies coming through. Swimmer is a step in the right direction, and we will be onboarding 6 new models over the next couple of years. So we're going to be busy bunnies here in the Met Office. but we are working with government to ensure that there is a programme of funded research into the future. And Night Swimmer, that will probably be largely what's called directed research. So rather than, whilst blue skies research is very important in this area, it's also important that we focus the research on the challenges we have, and the problems we have, and that's what we did with Swimmer, and what we hope to do with any future rounds.
Thank you. Question from Daniel Nutt, really technical, I don't understand it. Will the introduction of additional GNS dual frequencies, e.g. L5 frequency from GPS Navstar, in addition to L1, mitigate the impact on GNS availability? That's quite a good question, I think.
So dual frequency GNSS suffers less from the impact of space weather.
Fine, in a nutshell.
However, if the ionosphere is sufficiently disturbed, the signals will not get through.
Right.
Yeah, so if you're operating on single frequency, as you get an increase in ionospheric disturbances, you will see a degrading of your position accuracy. And that's one reason why we have things like EGNOS to sort of be reporting on such things.
UK aren't subscribing to EGNOS.
Yes, no,
so it doesn't really help
no,
us.
no. But obviously there is a UK government strategy for secure and resilient position navigation and timing. However, none of the current systems will operate through a very big storm. So you can so timing is the most resilient because you only need one satellite. But to get good 3D positioning, you need multiple satellites. Yeah, whether you're single frequency or dual frequency, the signals are not getting from the satellite to wherever you are. It isn't going to work. So,
yeah. Well, I think that again, Finland keeps coming up, but they seem to be withdrawing an awful lot of their ground-based aids and trying to move over to GNS approaches, as mostly in northern and remote airfields. And I think they're having looks like they may have to rethink that given the few outages had in recent times. Another couple of questions here. Are the Met Office working with the MOD, who have a £50 million project? And also, are they working with the National Timing Centre?
so I'll take those in reverse order.
Right.
National Timing Centre, no.
No.
But a lot of the work they are doing there is related to alternative means of timing other than GPS.
Right. Okay.
Yeah, so I know they're looking at things like assured UTC time over of optical fiber, essentially into critical locations. In terms of MOD, yes, absolutely. We work very close with the MOD in a whole range of areas. So we provide briefings into the Space Operations Centre within Space Command within MOD every day, and they act as, if you like, the front door for services elsewhere into MOD. But yes, we're very well engaged with MOD.
Excellent. Where we got? Oh, here we come. Hi, that's a good one. How can you become a space weather analyst?
It's probably a good one for Krista, seeing she is
I'll take that.
one. Yeah,
since that's what I did. So all our space weather forecasters are meteorologists who we train in space weather forecasting. So within the Met Office, we have meteorologists who cover a whole range of different sectors. Most of us, like me, start off doing forecasting for aviation. And then as we get more experience and sort of rise up the ranks of forecasting, become a senior meteorologist, you can choose areas to specialize in, whether that's World Area Forecast Center or shipping, or in my case, I went into emergency response, and that center who do sort of hazard centers, we call it, there's the opportunity to cross train as a space weather forecaster as well. So within the Met Office, we take experienced meteorologists and train them in the space weather, so they can apply that space weather knowledge to their existing forecasting knowledge.
And if I could just add something to that, Graham, just a point of interest for this particular community. So Chris talks about the Hazard Centre and the Environmental Monitoring Centre. So MOSWOC and what we call EMARC, Emergency Monitoring Centre, work effectively side by side, although increasingly it's in a virtual world side by side. So EMARC is back London, Volcanic Ash Advisory Centre for London. So our space weather forecasters are trained in volcanic ash, and our volcanic ash forecasters are trained in space weather. So if we were to get a big eruption producing a lot of ash in Iceland, and it was a quiet space weather day, the space weather forecaster would be assisting the VAC forecaster. And vice versa, if whoever's on duty, maybe Krista doing space weather, says, oh, it's next Carrington event, then the VAC forecaster would be assisting. So we've got them dual trained for resilience purposes.
Just looking at my questions here, they seem to be jumping around now. Do you do talks for other organisations or other government departments as part of engagement?
Yeah, we do lots of them, don't we, Krista? Particularly you.
Yeah. Yeah.
All the time.
Yeah, a whole range for different government departments wherever there's sort of the interest. Doing a lot of public outreach as well is quite a big part of what we do. I'm trying to think what I've even just done recently. I did a podcast a couple of weeks ago. I'll be doing something with one of our Met Office presenters next week, a deep dive into space weather. I had a radio interview a couple of days ago. There's a lot of interest in space weather at the moment, especially as we're coming up to solar maximum. Sort of the increased visibility of the aurora is really sort of sparking everyone's interest. So yeah, we do a lot of outreach, a lot of engagements, with different government departments and also sort of different sectors, and public outreach as well.
What I will add is there's only 3 of us that do it, so we have to manage our time carefully. So I won't make any promises here.
Yeah, I was just going to sort of come to that. It's obviously it's a huge subject, and it's becoming much more important, not just in aviation, but in the world in general. Are there plans to increase the size of your departments?
Yes, is the short answer. Yeah. So really the last 2 or 3 years since the update to the National Risk Register, the bit which happens within government actually occurs the year beforehand. So that was back in 2022. Since then, there's been a real drive across government for government and the sectors they manage to be far more prepared for space weather. So there's been a real uptick in interest, and that will result certainly in an increased ask for more funding, so we can get a bigger team. It's government funding, so we have to go through the standard sort of budgeting rounds. So we'll have to wait and see what the outcome is. But the ambition and the desire is certainly there, and we're hoping just to pick up some additional money for this coming year, just to accelerate the implementation of some of the swimmer output, particularly the radiation model that Krista showed.
Well, great. Thanks very much for all that. I think the questions have basically dried up now. If you get anything else you want to add before we wrap up?
No, I don't think so. Actually, having said that, I will just reiterate something that Krista said at the beginning of her section, is that it's probably been about 20 years since we really had a noticeable space weather event. So a lot of the systems we are using currently have never been challenged by space weather. This isn't a case of will it happen? Yeah, it's a case of when it happens. So there will be a big space weather event. We went through the whole of the last solar cycle, which was a massive underperformer in terms of space weather activity. So I'm just telling everybody they need to be prepared, essentially, because we know this solar cycle is running ahead of predictions. Those events back in 2023 that Krista outlined a big early part of her presentation, we saw as much activity in 2023 as we saw in the whole of the previous 11-year solar cycle. So I'm not promising there'll be a big event, but I'm just saying the environment has a habit of averaging itself out.
Yeah.
If we've had a below average one,
yeah, I know
we need to be prepared. That's what I'm going to say.
I know at BALPA we are quite concerned about the lack of preparedness that seems to be in aviation at the moment, as are our colleagues in Europe. And it's something we're actively working towards, try and get a greater sense of awareness through webinars such as this. So thank you very much again for taking the time to do these presentations for us, Mark and Krista. Thoroughly appreciated. And just a reminder to everybody who's watching in, this will be available on the BALPA website if you want to refer to it later. Thank you once again.
Okay, thank you very much.
Thank you very much.